Awesome. So quickly, we're going to talk about sort of what we learned. Let's start with these two balloons at the start. When we took these two balloons and rubbed them against our head, and then we took the two balloons and put them close to each other, what did we see? Or what did we feel?
Repulsion between the two balloons.
They were kind of fighting each other. They didn't want to go together, did they? Kind of like positive ends of a magnet or negative ends of a magnet. That's because the balloon, when you rib it in your hair, it strips electrons from your hair, making the balloon negative. And if each of the balloons are negative, bring them together, they're going to want to repel each other. We know that like charges repel, so that's a good start. Then session 2 was the hole punches, right? Okay, when we rubbed our hair on balloon and put it near the hole punches, what did the hole punches do?
They attracted towards the balloon.
They attracted toward the balloon. Why did they attract toward the balloon?
Due to an induction current.
It's called induction. What it is you bring a charged object near a neutral object, and it causes the charges in that neutral object to shift positions and creating a positive and a negative end, and thus an attractive force because the negative and the positive attract. Same concept with water, right? What did the water do?
Attracted towards the balloon.
It was attracted toward the balloon. Why was it attracted toward the balloon?
Oh no, due to
It was induction. Anybody else but this guy, okay? Yes. Anybody else but this guy. So what it is water's a polar molecule. Can anybody explain to me what that means? Yes. So it has a positive end and a negative end. If you're looking at a water molecule, it's going to have a negative oxygen atom and two positive hydrogen atoms. And it's built sort of like Mickey Mouse. You with me? Yeah. I mean, if we took this one and put it up here, it would be Mickey Mouse, right? Okay. But you'll notice that there's a negative side and a positive side. So since water is a polar molecule, if you bring a charged object near the neutral water, what it'll do is it'll align all of the positive sides all toward the negative thing because they're attracted. And the negative side is repelled, and thus we have induction happening, and an attractive force is created in the process, okay? What else did we do? We did the electroscope, same concept, right? Why would the electroscope allow electrons to flow throughout it? It's a conductor, right? A conductor is something that allows electrons to flow easily. In a metal, the electrons are allowed to kind of go wherever they feel like. They kind of move. So electrons are all move away from the negatively charged object, causing a positive side and a negative side and an attractive force. And last but not least, we got our cool little, these are Van de Graaff generators. And what we did is we created a situation where, look, it doesn't get charged until you touch the object, okay? And notice, what I'm doing when I'm touching the object is I'm giving this one, what? Electrons. And when I give it electrons, it makes it negatively charged. Since this is negatively charged, they repel, and there is a force that exists out there. Now, that force is not all that strong, right? But we'll talk about that. We're gonna do the math behind it real. So we've talked about forces before, right? Well, this is a force, just like any other force. Yes.
Is it possible for people to be overly charged with electrons?
Mm-hmm. Have you ever walked with socks on carpet and then touched a doorknob, right? That's exactly what's happening. You got too many charges, and you touch it, and it shocks you. So electricity is the flow of electrons from one atom to another. That happens in conductors best, things that allow the electricity to flow easily. Things that don't allow electricity to flow easily are called insulators. Okay? So be aware that's like wood and glass and plastic and rubber. We use each of these for different purposes. You'll notice we put rubber around all the wires on our plugs, and that's to prevent the flow of electrons to you, essentially. If we left exposed wires, that is that's a bad thing. We have things called semiconductors, which actually can do both. It can conduct electricity, or it cannot conduct electricity under different circumstances. And we actually use this to our advantage. We have things like silicon, which is what they make computer chips out of, that are semiconductors. And what we do is we put them under conditions that make them good conductors, and they conduct electricity, and that's a 1. And then we put them under conditions where they're not good conductors of electricity, and that's a 0. And then we end up with
1 0 1 1 0. It's binary.
What is this? Binary code, right? So that's what computer systems are doing, is they're essentially just reading whether something is a 0. It's creating circuits that are conductors and ones that are insulators, and then it sends a signal of sorts, of that sort, and each number has a binary partner and stuff, letters and stuff. So we talk a little bit about this. So conduction is the process of what I did is when I touched that foil, I did conduction. I gave that foil electrons, right, by touching the two together. Then what happened, so that is they were both charged and they were repelled. There's also a thing called induction, which you guys just did a lot of, right? It's creating a positive end and a negative end of a neutral object, and that creates a force that is attractive. I'm going to show you a quick video that kind of demonstrates induction reasonably well. All right. Should probably plug in the speaker, right?
Next, mix up some dishwashing soap and water. Lastly, get a drinking straw. To blow a large bubble, suck some soap into the straw and add it to your mouth, and then blow it gently onto the smooth surface. The surface needs to be coated in soapy water to form the bottom of the bubble. Now for the real fun. We need an electrically charged object. We can use the triple electric effect to charge a variety of different things. Try rubbing a balloon or plastic Coke bottle against your hair to charge the balloon or Coke bottle. A lot of different things will work. See my video about the triple electric effect for tips on this. Bring the side of the object that you charge near the soap bubble. The soap bubble is attracted to the charged object. If you come too close, it'll burst. Have fun pulling the soap bubble around or making it change its shape. Next, blow a smaller bubble in the center of the bigger one. Notice that when you attract the bigger one around, the smaller one doesn't move. Why not? Here's an explanation for all this. When you charge up an object, depending on the material you used, the area you charged either has more positive protons than negative electrons, like this glass, or more negative electrons than positive protons, like our plastic bottle. For our bottle, we say it's negatively charged. The soap bubble overall is electrically neutral. It has an equal number of positive protons and negative electrons. But it does contain impurities such as metals that are ions, i.e. they're charged either negatively or positively, and the skin of the bubble itself is charged. So while overall the bubble is neutral, the charge within it can move around, like with a metal object. With the soap bubble shown here, when you bring a negatively charged object close to the bubble, the negative electrons on the object attract the positively charged ions within the bubble, even some from the other side. That's because opposite charges attract each other. Now you have one side of the bubble with more negative charges than positive. We say it's negatively charged. And the other side has more positive charges than negative. We say it's positively charged. And just as like charges repel each other, opposite charges attract each other. So the negatively charged bottle attracts a now positively charged side of the bubble. It also still repels a negatively charged side of the bubble, but that's further away, so that repulsion is weaker. The attraction between the negatively charged bottle and the positively charged side of the bubble is stronger and wins. The bubble moves towards the bottle. And what about our smaller bubble that didn't move? It wasn't attracted because it's inside the bigger bubble, and the bigger bubble is acting like an electrically conductive container. It's a Faraday cage, which is the same as saying it's experiencing the Faraday ice pail effect. The Faraday cage protects objects inside it from external electric effects. It's the same thing that happens when lightning hits a plane. Passengers don't get shocked because the metal plane is a Faraday cage. The lightning affects the outer electrically conductive surface of the plane, but nothing inside. Another example is a dome on the top of a Van de Graaff generator. It's also a Faraday cage. So the soap bubble inside doesn't experience any attraction or repulsion of charge at all. Well, thanks for watching. Check out my YouTube channel, Star Org, for more neat science videos like this.
Yeah, buddy.
This is the one I mentioned about the triple electric effect.
So,
Is it? I mean, I'm not sure if it's common that like lightning actually takes.
Oh, all the time. It hits. It's yeah. The planes get hit constantly with the lightning.
Okay, you really do fly through the clouds.
So if we want to charge an object, we could do conduction, we could do induction, right? But we could also do static electricity. We could use friction to create static electricity. That's essentially what we used the whole lab, right? We kept charging the balloons. And how did we charge the balloons? We rubbed them against our hair, right? Well, what is happening when we rub them against our hair? Friction, good. What does the friction do?
It causes the balloon to be negatively charged. No, negatively charged.
Negatively? Yeah. Now, what it's essentially doing is the balloon is stripping electrons off the atoms in your hair. And when it strips electrons off the atoms in your hair, what it does is it actually creates a balloon that has an area of negative charge, And then your hair, because it's lost electrons, is now positively charged. And then the classic, oh wow, positive, negative charge, it's now attracted to that area of the balloon. And notice if I put it in other areas of the balloon, it kind of goes up and down because the attractive force is there. Thank you. Your hair's great, Caden. So we're gaining charge through friction. Friction is stripping the electrons. Why is this being so weird? There we go. Oh my Lord. There we go. So we talked about sort of the friction strips electrons from one object to another. This makes the object gaining electrons having an overall negative charge. The one losing electrons will have an overall positive charge. And we know that opposite charges attract. We also know that like charges do what? Repel, right? So two negatively charged objects will repel each other. And we felt that when we rubbed the two balloons against each other and we brought them close together. That's actually, there's a repulsive force because of that, okay? But we've also experienced this when two article clothings are in the dryer together, right? The sock sticks to the shirt, right? Well, why is that? Well, they're tumbling around against each other. And one of those, probably the sock, is stripping electrons from the shirt. And then the sock is now negatively charged. The shirt is now positively charged. And they are attracted to each other. Some of you have done this. We talked a little bit earlier about rubbing socks against the carpet. And eventually, when you rub socks against the carpet, you're going to gain a bunch of charge. And when you touch something that's metal, the electrons are going to flow from you to the metal, right? Because electrons, doorknob is metal and it's a good conductor. So these are all like basic electricity concepts that you need to understand. Now, we're also going to talk a little bit about the quantitative side of this. How do we, if there is a force that exists between these two objects, how strong is that force in comparison to what we really know? What do we measure force in? Newtons. And we're going to do that in the next notes, which is called Coulomb's law, okay?